Hello everybody, and welcome to ELEC 2210 Circuit Analysis 2. We're covering Chapter 14, Sections 1 through 2. Here's an overview of formulas and terms. A couple things to remember is angular velocity, which is the degree or radian, the distance in time. And then angular velocity could also be broken down to 2 pi, the frequency, or 2 pi over the period. And we're going to talk about inductive reactance and capacitive reactance as well. So there's 3 passive components in most electrical circuits: inductors, capacitors, and resistors. And so capacitors and inductors will cause a phase shift between the voltage and current when you're using AC. And also we're going to be able to compute capacitive inductance and inductive reactance. Capacitive reactance and inductive reactance. And those units are in ohms, and it opposes the current. And so we have to remember that capacitors and inductors are frequency-dependent devices. So how do resistors, capacitors, and inductors react to an AC signal? A resistor really is not affected by AC within reason, and we'll discuss that more later. An inductor current doesn't change instantaneously, and so therefore current's going to lag the voltage. And in a capacitor it's the opposite. Voltage doesn't change instantaneously, so voltage will lag the current. So a resistor is not affected by AC when we're talking about power line frequencies up to 100 kilohertz, so 50 hertz to 60 kilohertz, 50 to 60 hertz. That's for a purely resistive circuit. And we can use Ohm's law to compute current, the magnitude of current. And this is what we're looking at. Voltage equals the peak value of the AC signal times the sine of omega t, omega being the angular velocity. So just remember that voltage and current in a resistive circuit are in phase. However, in inductance, the inductance of the coil and rate of change of current are directly related. In an inductive circuit, the current doesn't change instantaneously. We have di dt. So current will lag the voltage, or you could say voltage leads the current, but both are by 90 degrees. And if it's a purely inductive circuit and you're trying to compute the inductive reactance, X sub L equals omega L, which is 2 pi the frequency times the inductor value in henries. So the higher the frequency, the greater the rate of change of current. And because of that, there's going to be a greater magnitude of voltage. So we can see omega there, being a component of the frequency, will increase the voltage. The higher the inductance also will increase the voltage as well. So we put here a 90-degree shift with the voltage because the voltage leads the current by 90 degrees. And don't forget, the plus 90 is on the left side of this axis. For an AC signal and capacitor, we have to remember that the current will lead the capacitor. And that's because it takes time for that voltage to charge up on that capacitor. And so a capacitive reactance is equal to 1 over omega c. And we can plug in 2 pi f for omega times c. So we can see here, as we increase the frequency, we can increase the current value as well. So let's do an example. If we have a resistor, a voltage, if we have a voltage in a circuit that's identified by this equation, 100 is the peak value, sine, this is the angular velocity, 377. So what is the current? It's just voltage divided by resistance. So if it's 10 ohm resistor, 100 volts, we get 10 amps. So we can just say, since they're in phase, it's 10 sine of 377t, and the voltage is 100 sine 377t, and here's the drawing of it. The voltage and current in a resistive circuit are in phase. Now, let's do another example, except we're not starting at the origin this time. We're starting at 60 degrees to the left of the origin. So find the sinusoidal expression for current when there's a 10 ohm resistor. So current's voltage divided by resistance. 25 divided by 10 gives me 2.5 amps. So if I want to write that for current, voltage is 25 sine plus 60, and the current will be the same except it's 2.5 amps. Sine of angular velocity plus 60. And here's the drawing of what it looks like, of the waveforms. Now if we look at an inductor circuit and we're given a current with a magnitude of 10 at the peak value of current here at the origin, there's no phase shift, and we're given 0.1 henries, first thing we want to do is find the inductive reactance, omega L. So we'll take this angular velocity times the value of the inductor, and we get 37.7 ohms. And then we're going to use Ohm's law. Voltage equals current times resistance here. The resistance is the inductive reactance. So we multiply 10 times 37.7, we get 377 volts. So we know that the voltage leads the current by 90 degrees. We're given a current starting at the origin, so we're going to add 90 degrees to that, to our value of our voltage in front. So there's our sinusoidal voltage, and here's what it looks like, the waveforms. Let's do another example with an inductor circuit. This time the current is at a minus 70 degrees from the origin. Find the sinusoidal expression for the voltage if the inductor is 0.1 henries. So x of L equals omega L. There's your angular velocity. Times 0.1 gives you 37.7 ohms. And so voltage equals current times resistance. So we have 7 amps that we have right here. That's the peak value times the resistance. We get 263 volts. We know in a coil the voltage leads the current by 90 degrees. So I'm going to add 90 to that, and we end up with this for our answer. The voltage is 264 volts sine 377 T plus 20 degrees. If we do a capacitor circuit here with 1 microfarad, the voltage is 30 sine of 400 T. X of C is 1 over omega C. And so we'll put in the angular velocity here times the capacitor value. And when we do our math correctly, we get 2.5 K as our resistance to current flow. Current equals voltage divided by the resistance. Resistance capacitive reactance, and we get 12 milliamps. We know in a capacitor that the current leads by 90 degrees, so we're going to add 90 degrees to that or the voltage that starts at the origin, and we get 12 milliamps sine 400 T plus 90 degrees. And here's our drawing. Let's do another capacitor example. 100 microfarad capacitor, the current is given here is 40 sine 500 T plus 60 degrees. First of all, we're going to find X of C. So we'll plug in the angular velocity times the 100 microfarad. If I do our math right, it's 20 ohms. Volts equals current times resistance. For resistance is capacitive reactance. 40 times 20 is 800 volts. So for capacitor voltage, the voltage lags by 90. So we're going to subtract 90 from this value here. So we're going to put our 800 volts sine. We're going to put the 500 T plus 60, but we're going to subtract 90, and there's our answer. 800 sine 500 T minus 30 degrees. So for homework in Chapter 14, do 5, 7, 9, 11, 13, 15, 17, 19, 21, and complete this by March 30th. Thank you and have a great day.